Hey everybody, today we'll do another video. Today we will do another problem on circuit. Um, Basically the power system area of the circuit, right? So it is going to be a kind of lengthy problem. Unfortunately, it's a lot. It can be done. That is the right. So basically we have a system, right, that we need to calculate some things on. So So we have panels, two panels, loads that are connected to a 240 volt RMS line, right? As shown in figure, that's the figure right there, put it right there so you can just look at it. Figure 1222 is that one. Load, load one draws um, 30 kilowatts, right? A power factor of 6 lagging, right? While load 2, right, this is a 2, right? Draws 45 cable, the power factor of zero point 0.8 lagging, right? This is doesn't make a lot of sense to me, but the book says it though. I'm not gonna, whatever. It is what it is. Because technical system then they don't draw K-bar. Right? What they do is they maintain the K-bar needed to other things that also is a power consumed and this is, and but it's not. They don't actually draw what they do. Like they take and give it back. They take and give it back when we're talking about positive and inductive loads. Now, unfortunately, that's what the book says. So I don't know. I just want to focus on the numbers. I don't focus on the word because words, you know, can sound beautiful sometimes, right? But not actually do benefits us, you know. In society right now, they will say that cancel culture is good, but not necessarily is good, right? And I'm sorry, I'm saying this again. I remember J M A Trump. So so I don't care. I can say things. And just because purpose, I am a Jesus first. So am Jesus follower. So Jesus follower. Then I am then I'm saying conservative, right? This is what I call conservative engineering academy. Thank you, YouTube. And I hope you get this YouTube. Thank you. But the reason because I need that, I will need that. I need this whole thing. We can do some some okay, so we have a lot to, right? Drop that. The power, like we said, lagging, right? When they lagging, assuming that they are in ABC sequence. Okay? This is the stuff that we need dealing with. This one. A. Determine the complex, real, reactive powers absorb, combine, right? The combined load. V, determine, right? B, uh, okay, B is determine the current, right? Okay, so B, the current, right? And the K-bar rating of each of the of the three capacitors, right? And then connect the delta, the cellular delta, well with the load, they will raise the P factor to 9.9 capacitance and the capacitance, right? And capacitance of each and capacitance of each capacitor. So, okay, so let's start it then. This is a big problem and I don't want to waste too much time. Right. So, okay, so now I think we can erase this because I have the problems you have to refer to. I have it in the book. If you wanted to, you to kind of go through this. Right? Maybe you can take it a screenshot if you want to do it on your own. Right? Okay. So, okay. So let's get this done. So there's going to be a couple steps to do this problem. I will not be doing every single step of it because I probably will take some kind of shortcuts to kind of get the problem kind of quick, but because it's kind of long. First of all, we need right for number one we have a given p, right? Given p is 30. So 30 p learn one p, right? Number one power, right? Power is equal to 30 kilowatts. And the cosine, which is cosine of data 1, which is the power factor 1, is equal to 0.6, right? So this and that, right? And then they say, right? Right? So also, if cosine is 0.6, then sine of data is equal to 0.8, right? But you can solve that problem in a different way too. I mean, I can show you now. You can actually do this different way. You don't need to do it this way. Even technically we deal with the cosine for the factor, even though they're related with the sine, but technically we do the cosine with the power factor, right? So now, so basically, this is this, right? And that is that. Now, okay, so let's do this. For the first one, we got just one, right? Because we are going to calculate the complex powers, right? So x1 is equal to, right? Find s1, the low one, okay? So which is going to be equal to p power 1, right? Which is this guy. Power cosine of data 1, which is that guy, which is that. So then this is going to be equal to 30 kV, which is 30,000, right? Oh, 30,000 divided by the cosine 0.6. 0.6. Okay, so when you get my calculator and do that, it's going to be 30,000, 30,000 divided by cosine of 0.6. Right. So 30,000. Maybe I don't have all the figures. 30,000 divided by, that's going to be equal to 50,000, right? Which can be reduced to move this to the left to reduce the numbers, and it's equal to simply 50 kilo kVA. Now kVA, right? 50 kVA, right? So that is one of the apparent powers that we found. Yeah, yeah. Let's get the other area, right? Which technically, so this is what I'm saying right here, right? You don't have to do this, right? You don't have to. What you can do to get more taste of the mathematics, you can say that data is equal to is equal to is equal to inverse, right? Cosine inverse of the angle of point of point of 0.6, right? Take that, right? And that is going to be equal to 53.13 degrees. Yeah. You will take this data and say, okay, and you say, okay, and now you say that, okay, so we know that this guy is equal to that, right, by this formula. Now I can say that, and I can say that Q, right, Q, right, Q1 is equal to sine of, is equal to, S1 sine of the guy, of data, right, which the inverse cosine over here, so it's 53.3, right? When you do that, you get that 50,000 times 53.13 is equal to 40. To 40, right? Now, this is K bar, right? This, actually, how to write this down then, right? So you add a J in front of it. Add a J in front of it. So the rate is going to be, it's going to be, it's going to be in the form of, as we know, it's going to be F1, right? Is equal to, it's going to be equal to the real power plus the imaginary part, right? Plus Q, right? Which is nothing but, so real power, right? So P plus J plus J, right? Or JQ, right? JQ is this guy that we found, right? This is only telling you that is imaginary. Imaginary power, right? It's going on right there. Okay, so dealing with, yeah, unfortunately, power triangle, all that. I'm not gonna deal with that right now. That's what it is. So technically, I can say that this guy is right here, 50 plus 50 plus 40 plus J 40, right? Why? Because Q1 is that one, right? So then 40, right? And and this is KVA. He told me it was going to be a KVA unit, but this is cable, right? So I want to make it sure that you guys understand that. But the system of those stuff of this whole thing is going to be KVA. So, of course, you need real part and you need imaginary part because, again, I don't want to go through this because we have a power triangle, right? We have an S, right, which is the one that we find, and we have P, and we have a Q, right? It's basically these two guys, Pythagorean theorem, a squared plus b squared is equal to c squared, right? Square that, and this guy is the sum of that, right? This is a c, right? So beautiful. I don't want to go through that too much because I don't have a lot of time. This is what is going on now. So we found the first one. Now let's do great. So let's do for the second guy. So so let's write this guy somewhere. 50 plus J 40 K B A. Now let's get it done. So that's the first one, right? So now what we can do, use what I did in this. I did not use this value. I took the inverse cosine of that. It used that cosine. I'm sorry. Take the inverse cosine of this and use the value that I got from this and then use Q is equal to S1 times the sine times the angle that I got from there, and I got the answer. Okay. Obviously, you can just multiply that one with the other one too, but again, for me, I like the better the taste of trigonometry to have a like more real feeling of it. Okay, so next, so we have a K-bar, right? So we have log 2, we have a K-bar. Log 2, Q is equal to 45 K-bar. So Q is equal to 45, 43,000 K-bar, right? What do we do with this? Okay, so same thing. You take the angle, right? So the angle that we got, right? So we say that cos. You can say that S is equal to Q over, we got a Q, right? Over the sine, the angle, right? So, which in this case, you can actually use the number that I show you. Okay? So you can say that 25,000, or 25 divided by sine of so point. So in this case, right? So you take that. You say, okay, so look at this point. So you got 45. So basically this is what you're doing, right? So you can do this a couple times, right? Now you take the inverse, right? um, to the inverse, right, of this value, right? So take the inverse of that. As you know that we know that it's 53, right? Now, now, now we know that if that is the case, we know that 45, 45 divided by divided by divided by oops, not the sign inverse. Divided by sine of 53. Point 13. Right. So basically what you're doing is in this case, right? So you got we know the angle of this is this, right? I'm sorry. The angle of this, we know that we take the inverse sine of this, right? To get the angle, right? Now you can actually do this by doing this. You can say that 45 over over 126 is equal to is equal to 75. Right. Okay. This is the new value. Okay. So now what we do with this? So we know that we have this value and also this is KB. Because this is KB, so this is going to be KB. Now this is KB. Sorry, KB. Okay, so now let's do this little quick, right? So now we know that 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 now after this, right? Considering the value of S2, right? Now you can say that S2 is equal to the guy, this guy, right? Is equal to actually do we call it S2? I guess S2. Yeah. I mean I don't mind calling S2. So okay, so so S2, right? So let me just do this again. So P is going to be equal to S2 cosine of the angle, right? Cosine, right, of the angle, right? What is there? So it is, in this case, 0.8. So if you take the inverse cosine of that, not the inverse cosine, but just the value, right? So if we do that, we replace 75 times cosine of our so so basically is so we know that we know right? So we know that this guy right here is the power factor given by that, right? So technically, this. Let me just do this. So if cosine is equal to the power factor 0.8, then I can say that cosine of data, making sure that, right? This is data. This is data. You can say that P, right, P2 is equal to S, which is 75, times the cosine of this guy. Times the cosine of this guy, which is what? Which this guy, right, was 0.8, which is the power factor, right? So now we're talking that we got a 60 kilowatts real power. For example, excuse me, but I got some cough going on. I don't know what it is, but it might be the CCP virus again. Um, just if you don't know about the CCP, stand for Chinese Communist Party, right? Anyway, so we do this, right? So now we got those values, right? Now we can say that 60, right? 60 plus 60 plus, and remember, we had already the value for the second look, right? We don't have to find that. We already the value, right? So the value for this first indeed 45, right? So the value in this is 45, right? 45K, and then it's going to be total. After we do that, it's going to be KVA. KVA, right? Yeah. So 45, 45, 45. Yeah. So this is the new one. So this is S2. Now they're asking now for the combined complex, right? We found S2, we find S1, right? So, so what we can do now is the following. So what we can do now is the following. So we can combine these two guys, right? So we can combine these two. We can say that S, we can call it as S total. S total is equal to S1 plus S2, which is equal to, in this case, we got 50, when we're 60, so 60 plus 50 plus, plus, plus 40J plus, oh, okay, I'm missing a J here. It's 45J, right? So 40J plus 45J, right? So then as total, as total, right? As total, right? Is equal to 90 plus 85, 85, right? KVA. Now we have the complex power. Okay, A is solved. A, put A. Okay, so that's A. And I don't know if my calculator went down here, but I heard something. Okay. Okay, so so that's A, right? We found A. Now let's find B. So B, they asking for B. They asking to find. They asking us to find. So the line current. Okay? The line current. They train now B, part B, oops, B, line current. Yeah. So line current, right? So looking at this, right? Looking at this guy, um, so 90, right? So 90 plus 85, right? So let's cut away back. Do the easy way. I'm not gonna complicate myself on this. Right? So not the easy way, right? This is stuff not easy. It's not too easy, right? At least I will try to cut in the work so I don't have to take a long time. So we know that this can be converted to a polar form, right? So what we do, we take we take we take the inverse tangent, right? First we can find the angle. We can say the tangent theta is equal to tangent inverse of real over sine over cosine, right? This is cosine, this is sine, right? So, and as long as this number is less than this, you're good. All right. So 85 sine over cosine, right? Tangent inverse, right? So tangent is equal to, okay, this is equal to sine over cosine, right? But I'm taking the inverse of those guys. So in other words, I am saying that, well, this is what I'm saying. I don't know if you remember from trig, but theta, tangent of theta, tangent of theta is equal to sine of theta over cosine of theta, equal, which is equal to tangent of theta is equal to y over x. Remember the triangle that I did? All right, so this is y, this is x, right? So this is what I'm looking for. Tangent sine or cosine, right? Sine or cosine, y over x. Okay, so okay. So I'm taking the inverse of that, right? I'm taking the inverse of y over x. So what is cosine? This is a cosine, and this is the sine. So I'm taking the inverse of that. That's why I say the theta is equal to inverse tangent of, of 85 over 90. So when I do that, so tangent is equal to 85 over 90, which is equal to 43, oops, 43.36 degrees. Here, 43.36 degrees, that is the value. Now, okay, so this is the angle now. I need to find the magnitude though, right? So I need to find the magnitude current, which is going to be equal to current I line current, is going to be equal to the magnitude though, so it's going to be 90 squared plus 85 squared, right? But taking the square root of those guys, right? So when I do that, I do 90 squared plus 85 squared. Right? Take the square root of that, and I do, you got it what? And remember, you can say this is a milliamps, right? I guess. 123.8 milliamps. I guess you can do that, I guess. No, be careful. Nope, this is not I, sorry. Nope, 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 nope. This is actually, I am converting, and I say that, but I didn't do what I said. This is still as total and polar, right? So this is nothing but kVA, right? kVA angle of, and this is lagging. So remember the power of that is a lagging. So negative 43.36 degrees. Right. Now, now this. How in that guy? What can we do? That's the question. So we know that we don't have to worry about too much different. We need to worry about this, and we know that ends is equal to v line, right? Or you can say b line, I line times the square root of 3, right? When we do that, we get that ends, that's, I'm sorry, this is, yes, right? So in this case, S total, so total, just total, right? Now, I'm solving for this guy, I'm solving for this. So what I'm going to do is manipulate this formula, divide this, right, like that, bring that underneath, and I get what? So now that this is this, right? So what I can do now, right? So what I can do now is 123, 123, 123, right? 123.8 equal to. So let me just do this real quick. See, let you guys clear what I'm doing. What I'm doing is taking this, divided, right? I am solving for I. So in other words, it's going to be as total, right, over VL times the square root of 3 is equal to IL. Okay? So when I substitute those numbers right here, I get IL is equal to 123.8 kVA divided by, so the value is 240, right? Is it 240? Yes, it's 240. So it's 240, right? 240 square root of 3 is 1.732, right? And that will give it the current. So divided by, so let's see. Okay, so divided by 240 times, so it's going to be very close. This one, I think I have to convert that to, hold on a second, let's see. So let's say 123, 800, okay? I move this to 1, 2, 3 places to the right, okay? And then I divide that by 240 times 1.732. Okay, so now IL is equal to 297.8 amps. I mean, 0.8 amps. Actually, it's milliamps. It's milliamp. Yeah, milliamps. Right? It's milliamps. So then we have B solved, right? B is solved. We have to do, and remember, this is what I'm talking about. The figure, right? So we have A. So now, well, this is A. This is A, and this is B, right? So B is this guy. Now, for B, let me put B here. So B is equal to I L is equal to 297.8 milliamps. Right. So we have those answers. Now we need to find the third answer. The third answer, they're talking about they're talking about having um so they're talking about getting the capacitance. So the capacitor, right? So this data, we will need that data, this angle right there. So, okay. So, so in other words, this also can be written in the form of like this, right? So, because we took the angle of, we need to like do 43.8 degrees negative, right? That's the angle. So, okay. And also the same, that is the same angle for the other power too that I found, but you know, we found the power just to find the current. But in this case, we're not keeping the other one. We're keeping this. This is for part A. This is for part B. Right. What I'm saying is, I converted that power into phasor, right? But it's not necessary, right? So, right. So let's get it done. So they saying that we need to find the capacitor, right? So we need to find the capacitor. So the capacitance, remember we need to find Q, right? Q capacitance, QC, right? I guess, I don't know. So QC, QC is can be written, can be found by this formula. So P, real power, right? Real power, engine, the engine of data, old, data, old, minus engine of data, new. So the QC, I don't need the QC. I guess I need quality control, right? Stand for? I don't know. I guess I guess Google and YouTube and Hellbook is kind of doing quality control on me, right? Like watching me what I talk about on this channel. If I talk about Jesus, I talk about, um, China virus and all that. Okay, it is what it is. I guess they're doing quality control. All right, QC. Now, this is the thing, right? So data new, we know that data old. So data old is this, right? So data old, right? Wait a minute. So data old is equal to 43.36 degrees. Data new, we need to find. Right? In the previous statement, we found that we knew that the power factor, the new power factor, right? The new power factor equal to zero point 0.9. So the new power factor is going to give us a new data new, this guy. So we need to find it. So how do we find it? So we say the data. Okay. So let me do it. So data new is equal to cosine inverse of what? 0.9 Yeah. Which when we do that, so cosine of 0.9 inverse is going to be 25.8. It's going to be 20, 25.8 degrees. So 25.8 degrees is a data nu. Now, following this formula, we say that QC, you took quality control, right? In Google, right? Quality control. Actually, they control it. People didn't even do quality control. Anyway, so QC, right, is equal to the power, right? So it's equal to the power that we found, right? And what is the power that we found, right? That will be the question. So so the power is not the power of this guy right here. So the power is that one. So the real power we're talking about is real power. Just real power. Real. So 90, right? So 90 tangent of 43.36 with data old. Data old. Right, data old. Minus tangent of data new, which is 25.8 in degrees, right? So when I do that, 90 strings, okay, parenthesis, tangent of 43.36, okay, those parentheses, minus tangent of minus tangent of 25, right? Close those parentheses. I get that. I get a QC. Okay. So QC is equal to 41 point something, 41.4, 41.4, K, K, so K bar. Look at that K bar. Look at that. This is for the whole thing, okay? So this is for the whole thing. You have to kind of consider that. So this is what I was trying to explain. I mean, I wrote the diagram right here. I mean, it's not really necessary, but these are the two load one and load two. And this is a capacitor talking about. I have three capacitors, right? Right? Three capacitors connected in parallel to the load. And this is what they're saying. They will improve the power factor by adding those three capacitors in there, right? So now let's get this done. So okay, so I'm going to write that on the top right here. We'll do some room. So we call it S total, right? S total equal to 90 plus 90 plus 90 plus J 85 kVA. All right. So this is part A actually. Anyway, so this is A, this is B, we're doing C now. So now look at this. This is the sum of our capacitor, but we had three, right? So what we can do is we can say that C individual, Ci, right? C individual, considers individually is going to be equal to QC, quality control, right? U2. Okay, so QC over what? Over 3, right? Why? Because we have 3 capacitors. And that is going to be equal to 41.4, 13.8. So 13.8 K bar, right? This is for each capacitor, right? So now that we have this Q capacitor individual, right? Or, you can say, whatever, QC individual. This is QC individual, right? QC individual is going to be equal to QC. You can take prime, right? Because you already found that, so it's equal to that. So this individual, each capacitor, let's take that amount of kV, the K bar. Now, what we can do next is the next step is just the last step. So based on the formula, we can actually, this formula, so it's called C is equal to Q is equal to Q capacitor, right? QC, right? In this case, it's QC, but it's QC individual, right? Because individual capacitor. So now that we have this QC, right? So we can divide that by omega, right? By omega times B R B is B square RMS. So when we get that, okay, so now, so what is omega? Omega, if you remember from my last video, I think I did a video on this. Omega is nothing but 2 pi times f, right? Times the frequency. And what is the frequency? So in the problem statement, say that f was 60 hertz, right? So now 60 hertz, right? So 60 hertz. What I can do here is replace omega by that, right? So I can say that C is equal to 13.8, right? K bar, right? So we're talking about K bar here. Now, it's in the probably I can have the omega, right? Which is 2 pi. So it's 2 pi. So that, okay. 2 pi. 2 pi times 60 degrees, I'm sorry, times, not 60 degrees, but 60 hertz. 60 hertz, right? And then multiply by what is the voltage, right? The voltage was 240 volt, right? So take the 240 volt times 240 volts, right? 40 volts square, And when you do that, when you do that, we get, we get 13 point. Actually, just change that to 13,800, right? T are divided by 2 by times 60 times 240 quantity square. So it's equal to point zero 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 0.006 355 and 1. So it's a very small number, right? So in technically capacitor, they have very kind of small capacitance, right? The kilowatt is kind of high. So now we can actually move this decimal point, right? 1, 2, 3, 4, right? 1, 2, 3, 4. Hundred and 6. Um, so did I do this correctly? Okay, so yes, maybe. Okay, so I needed to, so I put an extra, right? Extra 0. Yeah, no problem. So move 1, 2, 3, 4, 5. So technically is 3, okay. So this is nothing but, moving those lines to the right is going to be 635 picofarads. Okay, and let's see. Okay, so that is the answers, right? Those are the answers. So we have A, right? A is this. You have, this is not just part of the problem, but not necessary, right? So this is A, right? The combined complex power. This is A. This is B, right? And this right here is C. C, right? We can put C right here. So C is to 635 picofarads, right? 635 picofarads. Actually, they just put a decimal point there, which is fine. 635.5 pico. Okay, so those are the answer for that problem. Like look like an essay when I read it, but All right. So that's it, guys. Remember, Jesus is great, and that's why we learn every day. We learn something in this church. That's it. Jesus is good. Thank you for watching.